Hello everyone. So in this video, we are going to solve a problem using OpenFoam. The problem that we have chosen is is a flow past of square cylinder in which square is tilted at an angle of 30 degree to the incoming flow. So let me give you a brief introduction about the problem. So we have chosen a square and we have chosen a flow that is coming from minus x direction to the x direction, and in the flow path we have chosen put a square which is tilted at an angle of 30 degree to the incoming flow. So the rectangle is chosen so that such that the dimension of this rectangle is very large as compared to this square. So the governing equation that is involved in such kind of problem are Navier-Stokes equations, which are given by these two equations, and also the continuity equation, which is the third equation. The boundary condition that we have used here is that we have chosen that the flow is coming uniformly, that is it is uniform in the x direction with a velocity u naught, and v velocity is 0 at the inlet. And also there is no slip condition at the top and bottom boundary, and at the outlet we have assumed that flow is fully developed, and the boundary condition corresponding to that are these del u del x is equal to 0 and del v del x is equal to 0. That means there is no change as we move in x direction. The boundary condition for pressure, because pressure is also an unknown here, the boundary condition for pressure at walls are no gradient, zero gradient conditions, that is Neumann conditions, and at the inlet it is also Newman condition for pressures, and at the outlet we have chosen a Dirichlet boundary condition, and in which we specify that P is equal to P infinity, which is some reference pressure in this case. So this is all about the problem that we are going to solve, and we will show how to solve this problem using OpenFoam. So let me go to my Linux setup, and I'll open a terminal first. So I'm in my terminal desktop. So first I want to create a geometry about the problem, the physical problem that I have chosen. So in OpenFoam, what happened is that you need to use a third-party software to create the geometry. In this case, we are going to use gmesh to create the geometry. First, let me create a directory in which I'll save my geometry file. So I'll make directory OpenFoam and then demo. So now you can see that it has created a directory. It has created a directory in my desktop, and then I'll open this directory, OpenFoam demo. Okay. Now I will create another directory called geometry, GOMATRY. So now I'm gonna open this geometry directory. Okay. Now I'm going to open gmesh, GMSH. Okay. So I'm in my gmesh software. So first thing that I want to do is that I want to create a rectangle. I have already shown you how my geometry will look like. So it will look like this. So I have to create a rectangle and then a square, and then I have to rotate this square at an angle of 30 degree. So how we're going to do this in gmesh is that I first will create some points, that is the 4 vertices of the rectangle, and then I'm going to join all those points to make a rectangle out of it. So I'm going to go to geometry and then elementary entities and then add, and then I'll click on point. Then I'll add 4 points which are the vertices of rectangle. The first point will be 0, 0, 0, sorry, 0 0, then I'll click on add. Then next point will be 15 comma 0, so the x direction is 15 unit long. And then the third point will be 1510, so that my bidirection will be the width of that rectangle will be 10 unit long. Then 0 comma 10. So as you can see, I have added 4 points. Okay, so now I want to create the rectangle out of these 4 points. So what I'm going to do is that I'm going to join all these 4 points. So I'm going to click on line, then click on the first point, and then the point to which I want to join this point. So now you can see that I have joined a line between these two points. Similar, I want to do for all those 4 points. Okay. This point and this point, and now the last points. So now I have done with my rectangle. I've created a rectangle which is 50 unit long and 10 unit in width. So the next thing I want to do is that I want to create a square inside this rectangle. So I'm going to follow the same steps. I'm going to create points which are the 4 vertices of that square. So first point, so 1.5, and then I'll go 1.5 and then 4.5. Then I'm going to add this point. Okay, sorry, 1.5 and then 5.5, add 2.5, add, and then 4.5, add. So okay, now I'm going to join these points by using the option line. So I'm going to click on the first point and then the second point, and then third point. Okay, so now I've created a rectangle, a square which is 1 unit long. I mean its dimension is 1 into 1, because the length that I have chosen is from 1.5 to 2.5, which is 1 unit long. So the next thing that I want to do is that I want to rotate this square by an angle of 30 degree. So there are plenty of ways to do this, but the easiest that I can find is that, by the way, as you are following these steps, what gmesh is doing is that it is automatically generating a script which is corresponding to all the steps that you have followed. So I'm going to click on the option called edit script, and then it will open a script. So you can see that it has added of 0.1, 0.2, 0.3, and 0.4. These are the points corresponding to the rectangle, and then we have joined it by a line, and then okay. So what you want to do is that you want to save the script and then go back in gmesh. So what I'm going to do is that to rotate the square, I'm going to rotate all these 4 points by an angle of 30 degree by using this script. So what you're going to do is that you're going to write a command which goes by rotate. Then you're going to specify the points, specify the dimension around which you want to rotate these points. So in this case it is 0, 0, 1. So 0, 0, 1, and then 0, 0, 1, and then the center around which you want to rotate this point, that is 2, 5, 0, which is the center of the square. and then the angle by which you want to rotate this. So this is 5 by 6, and then which point you want to rotate. So in this case I want to rotate this 0.5, so this is 0.5, and then okay. So I'm going to save this script and then come back to gmesh, and then I'm going to click on the reload script option. So now you can see that it has already rotated this point by an angle of 30 degrees. So what I'm going to do is that I'm going to write the same command for all those 4 points. Okay, so points 5, 0.6, 0.7, sorry, 0.7 and 0.8. So I'm going to save this, come back to gmesh, and then click on reload option, and then now you can see that I have successfully rotated this square by an angle of 30 degree. Okay, so now that we have rotated this square, so what I'm going to do is that, oh by the way, this script that is called untitled, that means I have not saved it yet. So the thing I'm going to do is that I'm going to click on the save as option, then I'm going to name it as my geometry file. So this is named as geometry, so I'm going to save it. So now you can see that it is named as geometry.geo. Come back to my gmesh software. We have opened untitled geometry file in the gmesh, so I'm going to cut it, and then I'm going to open this file that is called geometry.geo. So I'm going to add gmesh and then geometry.geo. Okay, now you can see that I have opened the file called geometry.geo. So I can open the script corresponding to this geometry.geo, and then I'm going to geometry and then reload script. So I wanted to add a surface out of the surface on this geometry. So what I'm going to do is that I'm going to click on elementary entities and then add, and then plan surface. Now I'm going to select the boundaries. So these are the boundaries. Okay, so now I have selected the surface that I want to create. Now I can press E. So now you can see that it has created a surface. So this is a surface. Okay, now you can see the corresponding script. So now you can see that it has added a curve loop 1 and curve loop 2, and then it has created a surface out of it. Okay, so I'm going to save and then reload script. Okay, so the way OpenFoam works is that it solves the problem in 3rd dimension. Although our problem is 2-dimensional, but we are going to add a 3rd dummy dimension so that geometry is suitable for OpenFoam. So now I want to add a 3rd dummy dimension, the one I was talking about earlier. So I'm going to click on the option extrude and then translate in the Z direction. So it is already dz is equal to 1 and dy dx I'm going to keep it as 0. So I'm going to add one mesh layer, and then I'm going to select the surface. Now it has already created, so press E to end. So now you can see in the reload command that it has created a surface extrude. It has added an option called extrude 001 and then surface. So now I want to add a command here, which is layers 1 and then recombine. So in this way I'm recombine. So these are the commands that you need to add after the extrude option. So now layers 1 and recombine. Now you're going to save this and then reload script. Okay, so now I'm all done. So next thing that I want to do is that I want to mesh this geometry. Now you can see that I have added a 3rd dimension here. by the extrude command. uh, so next step that I want to follow is that I want to mesh this geometry. So I'm going to click on the option called mesh, and then 1D, 2D, and 3D. Now you can see that it has added uh, and some kind of triangular meshes in my geometry. So it is very coarse mesh that I want that at least around the square. I want some finer mesh. You can add refine this mesh by clicking on this option refine by splitting, but I'm not going to do this for the timing, because I want to refine my mesh around the square. So I'm going to click come in my script file, and then these are the 4 points corresponding to the square. Now you can see that these are the coordinates of these points, and there is an option called, and in the fourth place there is written 1. So instead of 1, I'm going to write it as 0.1. So it represents the characteristic length that the mesh is going to have around those points. So it was earlier it was 1. So now I'm going to add it as 0.1. So 0. For all the 4 points, 0.1, and then 0.1. So I'm going to save this and then save this. So okay, reload script. So first I want to negative this. So reload script. Now I have to mesh it again, 1D, 2D, and 3D. Now you can see that my mesh is very fine around the square, and the other point is it is still coarse. So I can make it finer by clicking on this option called refine by splitting, but because it will, computationally it will be expensive, and for this video, I'm happy with this mesh. Okay, so I've done meshing. So now I want to name all those four boundaries. Not four actually. Square is also a boundary. So I want to add names for all the boundaries, because I'm going to specify the boundary conditions later. So for that I need name of all these boundaries. So I'm going to select the option called physical groups, and then I'm going to add then the surface. So the first boundary that I'm going to have is called inlet. So I'm writing it as in. Then I'm going to choose the boundary. So this is my inlet boundary, and then I'm going to E. Okay, then I'm going to select the outlet. So out, and then I'm going to select the boundary, and then E. And then top. So I'm going to select the top boundary, and then E. Then bottom, and then I'm going to select the bottom boundary, and then E. Again bottom, then squares, because square is also a boundary, square, and then I'm going to select the square. You have to choose all the faces of the square, that is these and this. So now I have chosen the square, so I can to add E. Because we have extrude this geometry in third dimension, so these two, front and back, they are also a kind of boundary. So I'm going to name these boundaries also. That is front is this boundary, so E, and then back, 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 and then this boundary. So now I think I have named all the boundaries. So I'm going to come on to my script file and then reload this. Now you can see that I have added all the boundaries: inlet, outlet, top, bottom, square, front, and back. So these are, I guess, 7 boundaries. Okay, inlet, outlet, top, bottom, square, and front, back. Okay, so now I'm going to save this and reload my script. Now I have added the surface. Now I'm also going to add this volume because this is a 3D geometry. I'm going to name it as wall wall, and then I'm going to click on this wall. So now it is done. I can have a check on my script file. Now you can say that it has added a physical volume named volume. So I'm happy with that. Okay, so reload script. Reload script. Okay, so I'm done with my geometry. So next thing that I want to do is that I've meshed it, I guess. Okay, I meshed it. I want to save this geometry. So first I'll go to on the option file, then save mesh. Okay, then I want to export this geometry. So geometry.mesh. I'm going to export it as MSH file. Okay, I'm going to replace it. Then I want to save it in version 2 ASCII because that is the version that OpenFoam reads. So I'm going to click on the option. Okay. So now I'm all done. So you can see this is my OpenFoam demo directory. So this I want to delete this title. So I have created my geometry and corresponding mesh. I can read the mesh file. So I'm pretty much there. So as I'm done with geometry, the next thing that I want to do is that I want to open a terminal and set up my open fold structure for OpenFoam. So in this, I want to open a new terminal. Okay, new window. So in this, what I want to do is that the way OpenFoam works is that we need to choose a physical working example which is very close to our problem, and we are going to set a choose this as a demo problem, and we are going to implement the solver of that problem in our problem. So first I'm going to come on desktop, and then I have installed my OpenFoam in a folder called opt opt, and then click, and then I'm going to open OpenFoam 10. Now you can list all the file in this directory. So I'm going to open this folder called tutorials. And list all the files in this folder. So now you need to choose that what kind of flow that you are dealing with. In this case, I'm dealing with an incompressible flow. So I'm going to open this folder called incompressible. So incompressible, sorry. So incompressible, ls minus l. Then I'm going to choose icoform. And in the icoform there is a folder called cavity. So it is basically the standard cavity problem, and I will choose this cavity problem because it is very close to my problem. So I'm going to open this cavity folder. Now what I'm going to do is that I'm going to open this cavity folder to my destination folder. That is the folder where I've saved my geometry file. So I'm going to copy recursively cavity to my folder desktop to open form demo. Okay, so now you can see that if I open this directory, so now you can see that there is a folder called cavity that I have just copied. So what I want to do is that I'm going to open constant folder, and then I'm going to copy this file called physical property, and then I'll bring it out. Okay, and now I'm going to delete this folder called constant. I'm going to copy my mesh file, copy, and then I'm going to bring it here, because these are the tweaks that you need to perform because you are creating a geometry in another software. So these are the steps that you are going to follow. Okay. Now the next step that I want to do is that I'm going to close this terminal. Now I'm in my geometry folder, so cd backward, and then I'm going to open cavity. Sorry, cd. Now I'm in my cavity folder. So in this cavity folder, what I'm going to do is that there I have just copied a file, my mesh file. So I'm going to convert this file in OpenFoam readable format. So the command for that is gmesh to form, and then you're going to specify the name of the file. In this case, it is geometry.mesh. Okay. Now it is all done. Now you can see that here cavity folder, the constant folder is back, and in the constant folder it has created a folder called polymesh. So now I'm going to copy this physical properties file and put it back here. Okay. So the next step that I want to follow is I'm going to click on this constant folder and then polymesh and this boundary file. In the boundary file, it contains information about my boundaries that I have named earlier in my geometry file. So the first boundary is back, and first I'm going to remove this physical type for all the boundaries. Bottom, and then outlet square. So now I'm going to specify the type of this boundary. So back, the type for back will be empty because this is just a dummy dimension that we have added. So I'm going to keep it as empty, and the front also empty. And then the top, because it is a wall, and so I'm going to specify it as wall. And then inlet I will because it is not a wall, so I'll keep it as patch. Then bottom is a wall, so I'm going to write wall. And then outlet is also patch, and square is a wall because it is a solid boundary. So back it is empty, front it is empty, top wall, inlet patch, bottom wall, outlet patch, square is a wall. So I'm going to save it and then cut it. So now I'm going to open the folder called 0. In this 0 folder there are two files called p file and u file. So these are the boundary conditions for pressure and velocity. So I need to change this according to my boundaries. So first what I'm going to do is that I'm going to copy my boundary information from the boundary file. So I'm going to back, copy, and 0 file, and then u file, and then paste. Oops, I made a mistake. Constant folder, polymesh boundary, I'm going to copy it, copy, and then open 0 folder, u, okay. So the back, I'm going to, so back I'll keep it as empty, and the front it will also stay as empty. In the top, because it is a wall, so the type of boundary condition that I would like to specify on wall are no slip condition for velocity, so I'll write it as no slip. And then the inlet, because uh, at inlet velocity is uniform, so the type of boundary condition, it is a fixed value, so I'll write it as fixed. And then value, then I have to specify the value that I'm going to, so it will be value and uniform, then 1 0 0, sorry, 0. That means it is 1 in the x direction, and in y and z direction it is 0 0, because y component and z component of velocity are 0 0. Bottom, it is a wall, so I'm going to specify no slip boundary condition. I'm going to delete this. And outlet, for the outlet the boundary conditions are 0 gradient, because these are known type of boundary conditions, so I'll write it as 0 boundary condition, 0 gradient. And then square is a wall, so I'll write it as no slip boundary condition. Oh, sorry, no slip boundary condition. Then I'm going to delete this. Okay, so these are the boundary condition that I'm going to use. So I'm going to copy this, because the same thing I'll do for pressure file. So I'm going to go pressure, and then okay, so back it will, I'll keep it as empty, front also empty, top because it is a wall, and at the wall for pressure it is 0 gradient boundary condition, because it is a Newton type of boundary condition, so it is 0 gradient boundary condition. At inlet it is also 0 gradient. So fixed value, I will copy it as, because fixed value is for outlet pressure, because there is, for outlet pressure have different type of boundary condition. I'm going to specify uniform, and I'll specify the uniform 0, because I want to keep pressure 0 at the outlet. Now front back empty, top 0 gradient, inlet will be 0 gradient. So I'm going to copy it from here. Copy, paste. Bottom also 0 gradient. Outlet fixed value uniform 0, square also 0 gradient. So that is pretty much it. And now okay, in the cavity folder, now I want to use the option called check mesh. Check mesh is not found. Sorry, it is check mesh. No. So okay, so now I'm going to write a command called check mesh, and it said mesh okay, so it means everything is fine. Now we are ready to solve our problem. So I'm going to open this cavity folder and then system and then this control dict file. So it contains all the information about our parameter. For example, it is written here end end time. Okay, now I'm in my control dict file. So it contains the information about the parameter like time. So you can see an option called end time. So you can change it. Uh, so it specifies how long you want to run your simulation. In this case, I will set it as suppose 20, and my delta t. You can also change this, but right now I'm happy with that value. So I'm going to save it. And then what I'm going to do is that I'm going to run my simulation. Okay, now I'm in my cavity folder, so I'll write ico. Okay, ico form. So now you can see my simulation is running. It is solving something. Let me connect my charger. Okay. So my simulation is running now. My simulation has ended. So I'm going to open a terminal, new terminal. In new terminal, I'm going to open the folder cd desktop and then cd open form demo and then cd cavity, and then I'm going to open a software called paraform to analyze my output for post processing. So I'm going to open paraform. Okay, now I'm in my paraform software, so it has already generated a file called cavity.openform. So I'm going to apply this. I want to analyze my velocity profile. So the end time you can see here is 200. So I'm going to write the simulation. So here you can see that my simulation is running. And you can see that as I've used my course grid, so it is not that clear, but you can see that some of the vortex are shedding. Okay, so you can see that the vortex shedding phenomena is happening here. Now what I'm going to do is that I'm going to plot the glyph. So I'm going to apply. Now you can see the glyph and orientation will be along with the direction of u and scale u. So I'm just going to put it as 1. So apply. Now you can see how my velocity is changing, my u velocity is changing with time. So just I'm going to, so it is not clear, so I'm going to delete this glyph and then I'm going to run. So this is the overall simulation that we have simulated. Okay. Now suppose that I want to solve this problem for a longer time. So what I can do is that I'm going to go on my control dict file. So these are the file that it has generated. So I'm going to go on system and then control dict, and suppose I'm going to solve it for time period of 50. So I'm going to save it. Oh, sorry, cancel, and then come back to my terminal window and write ico form. So now you can see that it is already running my solver. So I'm going to let it run. So now my runtime has ended now. So I'm going to open Paraform again, and I need to analyze my results. So OpenFoam apply, and then I'm going to choose my U velocity, and then I'm going to run it. So I'm just going to delete this. Sorry. Delete this. So now you can see my simulation. So you can see that there are some vortex shedding happening here. So flow is kind of oscillating. So actually we can probe the location by clicking on this option called probe location. So I'm simply going to click on, so I'm going to apply. So now you can see that I've chosen a point, and corresponding to that point, it is showing the value of u velocity and the pressure values there. And you can see that it is changing with time because my flow is happening there. So now I just want to delete this probe location. Now you can see that some vortex being shed here because I have used a very coarse grid for computational purpose, for efficiency of computational cost. You can use actually a much finer grids to see much clearly that how these vortex are being shed. Okay. So this is our simulation for a square cylinder inside a cavity. Now, what you can also do is that you can actually plot data over the time. So for that, what you're going to do is that you're going to click on the probe option, and then you're going to select a point, for example, this point, and then you're going to apply it, and then you're going to click on the filter and then option, and search data over time. So plot data over time, and then you're going to click on this. Yes. Apply. Now you can see that and now you can see that there is some oscillation. So this is the p graph, and this is the u velocity graph. So now you can see that at the point that we have selected, so there is some oscillation, which is because we have put a cylinder in the upcoming in the direction of upcoming flow. Okay, the next thing that I want to show is that I want to know the effect of Reynolds number on these flow characteristics. So what I'm going to do is that I'm going to open my OpenFoam demo, and then cavity, and then my system file. a system file, and then control dict. Basically, control dict. So these are the I'm going to run for it 20 this. Okay, so I'm going to save it, and then physical properties. So I'm going to reduce the value of new, so it means that my Renault number will increase. And also in the boundary file, where's my boundary? So I want to increase the velocity, for example suppose 4. So now I want to see how my flow will behave. So I'm going to ICO and then form. Now I'm going to ICO and then form. Now you can see that solver has run. So I'm going to wait it for end. So I'm going to just close it. By the way, okay, so now my solver has run, and now you can see this. I'm going to open paraview, and then apply, and then hue. So this is the effect of increasing Reynolds number. I have decreased my viscosity values and increased velocity value at the inlet. So now you can see the flow is much faster as compared to earlier, and you can see there are more and more vortex being shed uh, in the flow. So this is the effect that I'm having if I increase my Reynolds number. Okay, so I'm going to stop it. So okay, so this was the effect of Reynolds number. So if I decrease my viscosity values and increase my velocity values at inlet, so this is the effect that we are going to see. We are going to see a more strong flow and strong vortex shedding around this square. So the other physical parameters that are of our interest are lift and drag coefficient around this square. So for that, and also the frequency of oscillation around the square. So for that, to calculate those lift and drag coefficient, we have to slightly modify our file system. So I'm going to click on this system file, and then this is the control dict file. So in this control dict file, I'm going to modify it, and I'm going to introduce two function. You can see the script. Well, you can find this script in OpenFoam help section. So I'm going to calculate this forces and force coefficient, that is lift and drag coefficient, and around the boundary called square. So I have named my square boundary as square. So I have written here as square, and then I'm going to save it. And then if I run this script, so another window. So I'm just going to, if I run my script now, ICO, form, and then you can see that it will produce a file called post-processing, and then which contains all the information about my drag coefficients and lift and drag coefficients. So just now you can see that it has calculated some pressure forces, okay, and then this drag coefficient and lift coefficients. Now what I'm going to do is that I also want to plot these values. So what I'm going to do, and for that I'm going to use a Python script. We have already written the script called plots.py and strohal.py. This Strohal number is basically the dimensionless parameter corresponding to frequency of oscillation. So I'm just will show you what are these files. So I'm going to open this file, get it, plots.py. Now you can see that this is a Python script, a very simple Python script in which I have given this force coefficient.dat file as input, and then I have plotted this. By the way, this when I run the code, it has automatically produced a post-processing file in which contains all the information about force coefficients and forces. So I have given this file as an input to my Python script. So okay, also I want to show you my Struhel file, struhal.py, and now you can see that I have calculated this frequency parameter called Struhel parameter, Struhel number, and then I have plotted it. Okay, now I want to run this Python file, so I'll just Python and then plots.py. Now you can see, so these are the my drag coefficients and lift coefficients. So you can see there is an oscillation here because our flow is oscillating. So I want to save this file, so I'll save it as lift and drag. So I will save it. Save. So okay, I want to replace it. Okay. Then I want to run my Struhel number file, struhel.py. Now it is showing the x value at this peak is 0.41. It means my Struhel number is 0.19. It is showing 0.16. So around 0.16 is my frequency of oscillations. So I also want to save this file and struhel.png. So I want to save it. Okay. So this is my frequency of oscillation at this peak. It is basically 0.16 in x direction. So it is showing 0.16 value. So that was pretty much it. So I hope you enjoyed this video. So thank you.